Alrighty, welcome back. Today we are going to start talking about coordination compounds, although I suppose we have mentioned them many times in the past. For example, we see that we can get a coordination complex like this. We've seen this complex ion before when we talked about KF, for example, formation constants for complex ions like this. We did see that this is a particularly favorable process. We saw that the KF is going to be very, very large for this. I don't know it off the top of my head, but it's a good thing, right? These make very stable complexes. How these actually work is you will have kind of your transition metal ion, and you'll have what are called ligands. And what happens is those ligands can... ligands always will have a lone pair, at least one lone pair, by the way. What they can do, and we can have another one on the other side or something. Is they will form a special kind of bond, which I'll denote this way. It's not a true covalent bond, but it is still stronger than your standard run-of-the-mill intermolecular force. We're going to see that this is something called a dative bond. And that always arises from this interaction between a Lewis base plus a Lewis acid. We can always think of our ligands, by the way, as Lewis bases. So the ligands that have these lone pairs are going to use them to kind of form these bonds to kind of a central metal ion. And so we're going to see that our ions are always going to act as Lewis acids, and our ligands will act as Lewis bases. Remember that the Lewis definition is all about lone pairs, so Lewis bases donate lone pairs to a system, and Lewis acids accept them. And so we can see that the lone pair from the nitrogen is going to go and coordinate, form a dative bond with the silver ion there, thereby forming the complex. And again, this is a super stable thing. So we're going to see these complexes are going to take... they're going to typically form because of these high constants. And we're going to see later on how we can get even better ones to form using our thermodynamics knowledge now. So... how these actually work, we have a couple of terms to talk about here. One of them is the coordination number. And that will be the number of ligands attached to your metal ion. And so, for example... not nitrate, and H3. We've already got the spam. I haven't even been streaming for like 5 minutes and the spam's already here. It has a coordination number of 2. I really just gotta put big follows in my do not allow as a word. So I'll put that eventually, I guess. So with this, we have a coordination number of 2 on this one for something like This one will have a coordination number of 6. For example, we'll have 6 water molecules attached to our cobalt. How that might look. Is kind of our typical sphere of hydration type idea, where when we had those ions dissolving, they did so because they would form these complexes. And so this actually, this is stuff that can form with all sorts of things, but we're going to focus on transition metals because that's the focus of this chapter, right? I mean, of course, we can have this happening with chlorine, or chloride rather, or sodium, and so we can have this sort of happening all the time. And then, how about another one? Let's do, what's a good square planar one? Platinum with 4 ammonias, okay. This one will have a coordination number of 4. So typically, you're going to see that with these coordination numbers, we know the geometries that would be associated with them. Obviously, we are not going to have lone pairs on our metal ions because those are going to have already lost electrons. We do see linear coordination complexes, though those are not. I mean, there's just a couple of examples of that. So the silver, diamine silver one is a linear one. There's not too many. Most often, though, we do see octahedral complexes. These are the most common coordination compound we're going to see. We're going to see that we can get either square planar or tetrahedral for if we have a coordination number of 4. So we're going to see that those are going to be the most common ones. Oh, I'm sorry, I put the 2 plus on the inside here. If we look at how these work, is we see that this is a complex ion, right? This is not a compound, it's an ion. We know that because it has a charge, right? Compounds can never be charged. They have to have a neutral overall charge. The absence of an overall charge, rather. But if we go ahead and stick some counter ions out here, now this becomes a coordination compound. Coordination compound. And so notice that these are counter ions here. They're there to balance out the charge. And we're going to see that the stuff inside here, in the brackets, is your complex ion. So how these might look, you'll have your complex ion formula in there. There, let's just say A minus or something. So how these will work kind of formula-wise is you'll have a potential positive counter ion, your complex ion, whatever it may be, and a potential counter ion. A potential negative counter ion. So you don't always have these. Sometimes you'll have positive counter ions. Sometimes you'll have negative ones. Sometimes you won't have any counter ions. But that's how something like this would look if you have examples of these. I can give you a couple more. How about we do? Yeah. Well, I mean, those are all water-based. Who cares? Let's actually take a look at these. So these are two coordination compounds that we have. What we have here is a little bit of a difference between them. We have a cobalt and ammonia complex with 3 chloride ions acting as counter ions. In the second one there, we have a complex between cobalt, ammonia, and chlorine. And then we have 2 chlorine counter ions there. So here we have 6 ammonias that are bound in the complex. And then we have 3 chlorine counter ions. However, if we change up our conditions, we might end up with a different complex. Whereas this one has 5 ammonias that are bound in the complex. We have 1 chlorine bound in the complex. And then we have 2 chlorine counter ions. We have another name for this stuff, by the way. This is called the coordination sphere with extra R's at the end. The coordination sphere is going to be everything that's stuck onto your central metal ion, including the metal ion. So that's going to be everything that's there. Counter ions are not part of your coordination sphere. What's important to know is that if we were to dissolve these compounds, most of them would be soluble because they're ionic, right? We're going to see that counter ions will just dissociate away. They'll go float off into solution elsewhere. But things stuck on your coordination sphere do not dissolve. They don't break off. So if you were to take this first compound, let me just copy it, and dissolve it, you would end up with your complex ion. What's the charge of this, by the way? Hopefully we can tell that this is a charge of 3+. Obviously we have 3 chloride counter ions, telling us that therefore it's going to be a 3+ charge overall. So when you dissolve it, you're going to end up getting your complex ion as well as your counter ions separating from each other as you dissolve it, if it's aqueous. If you take the second one, though, and here, I'll just copy it. If we take this compound and dissolve it, we get different no, that's only 2+. Yes, right, yeah. We're only going to have two chlorines dissociating. We're going to end up with a different complex ion as a result. Yeah, and it's going to be +2 because we have one of the chlorines there. So we're going to see later on how to predict the charge of these based on like some common ligands that we have. What's interesting to note is that these will have different properties from each other. For example, this one is bright orange, but this one is bright purple. So we're going to see that the ligands that are stuck onto your metal are going to end up changing its properties, of course. So it just depends what's stuck on datively, like kind of covalently, and what's just there as a counter ion will have different effects on your solution. That's the reason these things were kind of discovered, is because there's all these very vibrant colors associated with them. We're going to learn, if we get today to crystal field theory, we'll learn how to kind of associate the colors with some of the transitions that are happening with the d electrons. But remember that it's the d electrons that are moving around that contribute to colors. because those energies are in the visible light spectrum. Anyways, what was I going with this? Okay, so that was the vocabulary stuff. With these, we can now talk about various ligands. And we're going to see that most ligands are either going to be neutral or they're going to be negatively charged, because remember, they do have to have a lone pair. Something that's negatively charged will have a lone pair, right? So we're going to see that that's going to be the case. So we have a lot of potential ligands here that we're going to talk about. And then we're going to talk about naming coordination compounds. So we have, of course, our halides. Which, just X minus, typically used for halides. So we have the 4 halogens that we could use. And we're going to see that. Let's kind of make this into a chart, I suppose. So let me, let's move this off here. So we'll go kind of with the formula, the name, and kind of the charge. Is that something we want to? And then we'll talk about denticity. Another fun word. Okay, let me step back. We'll talk about denticity real quick. So sometimes you'll have, or rather, let's do it with your ways of talking about it. This is a compound called ethylenediamine. This compound is covalently linked together, has the 2 carbons and 2 nitrogens there. It has 2 bonding sites that it can bond with a complex from. We would call this a bidentate ligand. Dentate, like dentistry, means teeth, so it's got like 2 teeth that it can clamp onto this cobalt. We're going to see that other ligands can be tridentate, and then we just kind of have the category of polydentate for everything that's greater than 1. So we're going to see a lot of ligands will be monodentate, and then the others will be polydentate, which could include bidentate or tridentate or others. We have hexadentate ligands as well. So we have all sorts of ones. So let's erase that for now. So we're going to have our kind of halides here. So we've got iodine, chlorine, bromine, and fluorine. All of these are halides. We're going to see that when we name complex ions, we're going to have to adjust the name of our ligands slightly. In a coordination compound, all of these are just going to become O ending kind of prefixes. The charge of all these ions is -1, of course, that for these ligands. And these are all monodentate, meaning they have one place they can bind. And that makes sense because they're individual single atoms, right? And so they should only be able to bind kind of once to something. All right. We have a couple more ions here. We have nitrite, which in coordination compounds becomes nitro. And it's also monodentate with a -1 charge. We have OH minus, which is going to be hydroxo. So again, these are pretty much, you're noticing the endings are all O's, right? So it's kind of just removing our suffixes, the "ide," the "ite," whatever it may be, replacing it with the O. That's another one. That's monodentate. We have this mysterious substance. And interestingly enough, it takes the name aqua in coordination compounds. It does not have a charge, so it doesn't mess with your... doesn't affect your charge. It's a monodentate ligands. Monodentate ligand, rather. Ammonia is another very common one. This one is special. It takes amine as its name with 2 M's there. So we're going to see again shortly how to name all these, but we have to kind of give you the list of all the common ligands here. We have this guy, which is called pyridine, which we usually just write as PY, or we can just leave it as pyridine. So if we're writing a formula, we'll often say PY, but if we're going to like fully write out the name, we're going to keep the pyridine. I don't know how to spell. And that's just like benzene, but it's got a nitrogen stuck in there. And so this one will become pyridol. This is a convention that comes from organic chemistry, so we'll learn that later on next semester. But that's another one. We have bipyridine, which is Bipy. Bipyridine is 2 pyridines put together. Oh my gosh, I'm terrible at drawing this. Does it have the third one in the middle? Or is that phenanthalene? No, it's phenanthalene. Bipy is, it's just the 2 of them, I think, yeah. Yeah, Bipy, of course. That one will be Bipyridol. This is a bidentate ligand. Remember that bi falls under this category of poly. Let's see, what else do we have? We have ethylenediamine. Which we abbreviate N. We do not change the name for this guy, so we just keep it as ethylenediamine. No charge, but it is bidentate. It's got the 2 nitrogens there that we have. Let's see, how about... Oh, phenanthalene, of course, yes. Phenanthalene is very similar. Actually, let me draw it this way. This is 110 phenanthalene. You don't need to memorize these names, please don't. But these are just common ones that we see. So, if we were in person doing these, we would be using actually the phenanthalene in some of our experiments, doing spectrophotometry with iron, because it complexes well with there. The name is still the same. No charge on this, but it is bidentate. We have just a few more that are a little bit easier. cyanide, which, like the rest of them, will go to cyano. And then we have carbon monoxide, which takes the name of carbonyl. No charge, and it's monodentate. Woo! Quite a lot there. So these are common ligands that we're going to see with this. And so we can look at these, and we're going to learn some naming rules with when to use them. So for just a complex ion, let's take a positive complex ion. Like for EDTA, we'll talk about when we talk about chelating agents. But EDTA is, yeah, definitely a common one. That one is a hexadentate ligand with a -4 charge. But we'll get there. What was I saying? Oh, yes, naming these ones. So let's take this lovely complex ion here that I can't seem to remember to put the charge on the outside. How we would name this one. I'm going to give you a couple of examples with the names, and then we'll talk about the rules for the names. This one is hexa aqua cobalt 3. This one is pentaamine chloro. What's it? Cobalt. And so, when we are looking at naming these, the first part of it is we say all the ligands in alphabetical order. So whatever your complex happens to be, you're going to name all of your ligands in alphabetical order with prefixes. For how many of each ligand you have. So that's why we had pentaamine chlorocobalt. So we have 2 different ligands on the second one. We had 5 ammonias, 1 chlorine. Amine comes before chloro. So we are going to put amine first, and we're going to put penta to signify that we have 5 amines on there, 5 ammonias. We're going to just not worry about mono for these, so you only need to put di, tri, tetra as those go through. And then the second part of the name creature, what are you doing? Making all sorts of weird noises here. Relax, buddy, you're okay. Is you're going to put the transition, or the metal with its charge. And that's going to be with the Roman numerals. So let's take a look at some of the other ones we've got that we've put out there. And then we'll do a couple more examples. Actually, I guess we didn't really do anything besides this. Oh, here we go. Yeah. So we'll do this one. So this complex ion, we'll name it. We see we have tetra amine, platinum 2. The not ammonium there. What am I doing? Ammonia. Notice that the ammonia being a neutral ligand does not, the number of ammonias does not matter when we're looking at our charge, because each of those ammonias has a charge of 0. So the 2 plus comes entirely from platinum, so that's how we know it's platinum 2 there. So that's how we're going to have that. What else did we do with these? Oh no, go away. We did platinum, we had cobalt. I guess we have the silver we can talk about. This is just diamine, silver. You don't technically need to put the charge here because we know that silver only takes the charge of 1. So just like before, if you're dealing with zinc, silver, cadmium, we don't have to put any charge there. So it's just for the ones that do take variable charges. All right, so let's, how about we do another one? How about this one? Well, so let's take a look at what we have here. We have amine, we have aqua as our ligands. Amine comes first, alphabetically speaking, so we're going to do that one first. And so this will be tetra amine diaqua copper 2. Yes. Very nice. Let's see if there's other kind of good examples here. Actually, I have. Let's have a look. Let's do another couple of these. Old exam. Okay. Let's do no, I can't give you that one yet. Okay. Let's do this one. Let's take look at how long these names get to be. This is at the point where you're going to look at the back of your shampoo bottle and you'll see all these crazy names like this. So, if we're going from the name into the formula, of course we have chromium. We always put the metal first in our complex. We have 3 amines there. We have 2 waters. And we have a hydroxide. The amines and waters are neutral, so they don't change our charge. However, the hydroxide is a -1 charge. So if chromium is +3, we have 1 hydroxide. That means overall, this complex ion should have 2 charge, +2 charge at the end. Alrighty. How about this one? Oh no, I can't give that one to you yet. All right, fine. I'll tell you our kind of next kind of thing here. If a ligand is polydentate, we use different prefixes with those. We use special prefixes when we're dealing with polydentate ions. Just because polydentate ions often include Greek prefixes already. For example, we have seen ethylenediamine. It already has a di in it. And so instead of saying if we have two of these, we don't say diethylenediamine because that would be a little bit confusing. So what we would say is if we have two of these, we say bis ethylenediamine to indicate that we have two ethylenediamines, not two ethylenes, two amines. So just to eliminate confusion, because most polydentate ions include a Greek prefix already, we throw in a different type of naming convention here. So if we do this, let's take a look at what that looks like. Actually, I guess this example does not have that. But we will do one next that does have something like that. All right, so if we're going to name this guy, and let's also, okay, let's do this one first, yeah. If we do this, this is going to be, we have to take a look at our naming of all these, right? This is ethylenediamine. This is amine. And this will be bromo. So we have to do these in alphabetical order, right? So we can do that. Our metal, by the way, is rhodium. That's RH. Or is it rhenium? No, rhenium's Re. Oh, wait, no. What am I saying? Metal goes at the end. So we're going to have triamine, bromo, ethylenediamine, rhodium, 3. So it's just a matter of having all this fun stuff, have a chart of this crap here that we can have all these put together. If I change it slightly, we have the same things here. This one would be named amine, bromo, bis ethylene diamine, rhodium 3. So these names get long and tedious, but that's okay. fun. All right, how about we do one more? So sometimes, by the way, you'll see these with hyphens. Sometimes you'll see them with parentheses around. And let's see. What shall we... Oh, that's going to be a negative. Oh, no. 2 minus... Let's see, what can we do with this? Yeah, we'll do it this way. All right. We've got this thing. So... Where are we here? Typically, we do put these in the greatest number first, and then the rest just kind of in alphabetical order. I guess I didn't necessarily say that, but you'll see that the things that we typically put on are going to be in order of how many there are, and we typically also put polydentate ones first. So let's do that. So we're going to put and then after that we're going to do them kind of in order of how many alphabetically. So with this we have manganese, right? That's going to be our metal. We're going to have, we have a polydentate ion here, the oxalate ion, right? So we are going to have 2 oxalates. We know that because it says bisoxalato, oxalato. I don't know how to actually say these things. I do not deal with this chemistry at all. Then we'll have our ammonia and our chlorine here. If we look overall, our charge for this is -5. We have manganese 7 though, so we still have 2 plus here. Alrighty. Questions on any of these so far? Oops. Alrighty. So the kind of other thing we have is these have all been positive complex ions, but we do have negative ones. And actually, do I want to do iron? It's kind of a crappy... Okay, well, whatever. I guess I have no choice. This is a very common one anyway. So with this, we're going to see that this would be hexacyano iron 3, right? That's how we would normally expect this. But how we'll actually do this is instead of writing iron 3, we write ferrate 3. So iron's a bad example because that one does have a name change. It goes back to its other one. We will see that copper will do the same thing. It will go to cuprate if you have it in a negative complex, or really any of the ones that have kind of the common names, like where their symbol doesn't match their their name that we have now. Like orate would be another one. You'll see that these will have that 8 ending. But let's see one that doesn't have something like this. Let's see. They're all ferrates. Okay, how about this one? Yeah, we'll do this one. How many waters? All right, naming this guy. As always, we'll go alphabetically here. But we have 4 hydroxides. Okay, whatever. I'm not even going to touch that. All right. So with this, let's go for it. We have aqua. We have hydroxo. Those are our groups that are on this. And so what we're going to do is name this as always. So we have diaqua. We have tetra. I don't know how to spell tetra. Hydroxo. Aluminum 3. That's how we would normally name this, right? But since it is a negative one, we will change it to aluminate instead of aluminum. Just changing the ending there to 8. And we'll end up with our name for this complex. Aren't these fun? Alrighty. If we have counter ions, by the way, so now that we actually have, now we're actually going to be dealing with compounds now, we would name cations first, then the complex, and then we'll name anions. For example, well, let's take a look at what we have. We have oxalate in there, right? So we'll have oxalato. We have vanadium in there. We have 3 oxalates, so that's -6. The potassiums will give us +3. So overall, our vanadium is +3. Hopefully that we can tell as well. So we are going to call this potassium tris oxalato vanadium. Actually, since this is a -1, we'll have to call it vanadate 3. Yeah, very nice. So we do say vanadate though, because it's vanadium. So we still have yeah, there we go. Fun stuff. How about lithium? Let's see, what can we do here? No, let's do diaqua. Bromo tetrahydroxo orate. Okay, let's do something like this. Foul compound here. As you can see, these rules are terribly, or these names are terribly long and confusing. But for whatever reason, we have to learn how to name them. So there we go. Let's do the complex part first, and then we'll put our lithium at the end. So we won't worry about that. So orate, that tells us we have gold. We have some hydroxys, some waters, and a bromine. If we look at this, we know this is going to be negative overall, but we don't know how negative. We know we have 4 minus from the hydroxides. We have 1 minus from the bromine. We have 3 plus from the gold. That's what the 3 tells us. So overall, that's minus 2, right? So that means we need 2 lithiums out front to balance it out. Yeah, so because this altogether was minus 2, we're going to need 2 lithiums to balance that thing out. And we'll have made our crazy complex. I guess I've given this 7 things. Whoops. Oh well. Again, this is the problem when I make stuff up, so oh well. Alrighty, any questions on these? So, naming these is annoying. But that's okay. By the way, if you do see... I think we did have it here. We had NIA, so... you'll sometimes see those abbreviations as part of these as well. What else do I want to talk about here? No, I think we're good. So we've had all this fun sort of naming stuff here. We have a little bit more to talk about with the naming when we talk about isomer types. So we're going to throw cis and trans in there occasionally as well. That we'll deal with. Actually, I do have time for that. Yeah. Let's do it. I kind of don't, though. Well, I'll give you one example. So, Octahedral Complex. You don't have to write them the way that I'm doing it. In organic chemistry, we always talk about the... you'll see that I'm writing my ammonias backwards here. The reason for that is because it's the N that's bound to the cobalt here. I want to show that the N is the closest atom to the cobalt. That's why I'm writing it this way. That's why you'll see sometimes, like if it's hydroxide, I'll write HO instead of OH, or water, I'll write O2H or something, or OH2 rather, just to like show that in all of these cases it's the nitrogen that's attached to the cobalt. That's something that I've done that's in organic chemistry. I'm used to doing it that way. I don't mind if you have them all as NH3s. That's not a problem with me. This, by the way, we'll see that this is cis. This is trans. The rules for this we have there on the opposite sides here, the chlorines. When you're looking at what's going to be trans or cis, we look at the highest atomic number. So while it may not be super obvious in a octahedral complex like this that those two chlorines are on the same side, if we were to like really 3D do this, we could. We can see the chlorine is sticking up and down. It's easier to see the trans isomer here. We can see that the chlorines are on opposite sides of each other in this. But in the cis one, there's only a 90-degree angle between them, whereas here we have 180 angle between them, if we remember our geometry here. Assuming these are, normal octahedrons, we don't have any distortions happening. And so we're going to see that these will have different properties. And so I guess I shouldn't have started talking about this because we have to talk about polarized light and all that sort of thing. So never mind, I guess. But suffice it to say that you can have the same formula that ends up giving you a different complex compound. And so we'll, I guess, deal with that next week. So we'll be done for this. So we'll just end here today then. So let's see, any announcements? No, I think Monday we'll just continue on as always. So nothing crazy surprising there. Honors people, I'll see you tomorrow for our last meeting. And yeah, that'll be it then. All right, have a great weekend. See you guys next week.